What I want to talk about today is alkyl halides. This is continuing what you might have seen already in an earlier video, but I want to talk about their reactions, the chemical reactions that are characteristic of alkyl halide compounds. So just to remind you, the code that we use, for example, would be something like this. I think this is the same compound that I used before. That would be 1, 2, 3, 4, 5. That would be 2-chloro, 4-methyl pentane. And all of the information that's of importance right now is that when we have a carbon to chlorine bond, or carbon to fluorine, or carbon to bromine or iodine, we have an alkyl halide. And as I pointed out in an earlier video, a carbon to halogen bond is polar. Some values of electronegativity, that is the Pauling electronegativities. And iodine is 2.7, but I don't have room for it. So a carbon to fluorine bond has a difference in electronegativities of 1.5, where the fluorine is the more electronegative. Chlorine is 0.7, carbon to bromine is 0.5. In every case, the halogen is more electronegative, which means that electron density is sucked away from the carbon that's represented by that spot there. So we sometimes draw just an arrow on top of the bond saying the electrons are being pulled towards the halogen. And all of that makes, this has profound consequences for organic chemistry, it makes that carbon, it gives it a character that's called electrophilic. It feels itself hungry for electrons. So it attracts an electron-rich species to it. And what I want to do now is talk about the language, how electron-rich species are identified and what they do, which are the reactions. What Janice Smith, and I really like this book, but I'm going to be critical of this chapter and the language that she uses. The language that she uses is pretty much standard, but it's confusing. I think I can make it simpler. First is this term that becomes cliche in organic chemistry, a good leaving group. It's never defined really, except you're supposed to, I guess, figure it out from all the context that is used. But in this discussion, a compound like that has a carbon to halogen bond is said to contain a good leaving group. Well, a good leaving group is exactly that. It's implying that an organic compound with a good leaving group is one that it's willing to let go of. The organic compound is willing to let go of. And it turns out that a chlorine nucleus and the 2 electrons that bind it to a carbon, so chlorine plus 2 electrons, which means chlorine as an anion, chloride's a good leaving group. What that means is it's willing to let go of the carbon in the right circumstances. What Janice Smith uses, which is standard, but I gotta say I think it's kind of misleading, is a statement like this. This is from Smith. The more stable the leaving group, X with a pair of electrons minus, X minus, the better able it is to accept an electron pair. She says the more stable, she doesn't define what stable means. So in what sense is an anion stable? Really, not very many senses is an anion stable. What I think would be a better phrase is that the more electronegative the element, the more likely it is to form an anion, and the tendency to form an anion is a measure of how willingly, how easily the anion will separate from the carbon. That makes it a good leaving group. Then there's another sentence, which again is kind of typical of almost all these textbooks, but difficult. Here's a sentence. This is again from Smith. In comparing 2 leaving groups, the better leaving group is the weaker base. I really think this is a remarkably bad sentence, because we've spent kind of in recent weeks recent days effort to define what a base is and what an acid is. Remember early in the term, I said we've got to get familiar with this table of acid strengths and the way the tables are always constructed. The strongest acids are at the top, and we come to understand that an acid will always have its deprotonated form, which is called its conjugate base, and the stronger the acid is, the weaker the conjugate base is as a base. And in the contrary, the weakest acid will have a very strong conjugate base. So we defined all of acid and base in terms of ability to either hold on to or let go of a proton. And now it's being used to say, hold on to or let go of a carbon. That I find confusing and a little bit silly. I think we might say that the tendency, the electronegativity, the willingness, the tendency of a halogen to receive a negative charge, to accept a negative charge, which is really a measure of its electronegativity, is also a measure of the ease with which it might let go of a carbon, break a carbon to halogen bond, and leave as a chloride. So now there are a couple of other terms that are really the heart of what I want to talk about this afternoon. First is the notion of a nucleophile. And again, I'll reiterate what you already know, a base. Now these two terms, they've got a lot in common. I would like to propose to you that you understand this and kind of say this in your mind, if not out loud, when you come upon the word nucleophile. A nucleophile is a chemical species that's got a pair of electrons available, an unshared pair of electrons, so they are available for forming a bond to a carbon. When all of that is satisfied, that chemical species can act as a nucleophile. Now, a very similar chemical species might have a pair of electrons, but if it uses that pair of electrons, if the chemical species has a pair of electrons available for forming a bond to a proton, that chemical species is acting as a base. Now, the reality is that a chemical species like this, CH3O minus. Now, I'll draw on the unshared pairs on the oxygen. The oxygen has 3 unshared pairs and a negative charge. This is called methoxide. Methoxide is a perfectly fine nucleophile. It has, in fact, not just one, but it has 3 unshared pairs of electrons. It can use any one of them. They're all equivalent. It can use any one of those pairs to form a bond to a carbon. And there it is. Methoxide would be acting as a nucleophile. If, in a different circumstance, methoxide used its unshared pair of electrons, any one of its 3 unshared pairs of electrons, and used it to abstract a proton from an organic molecule, methoxide would be acting as a base. So the distinction between nucleophile and base, what I'd like you to understand, is really in their behavior, not in their composition. Often, a chemical species, generally a chemical species that could act as a base, could also, in different circumstances, act as a nucleophile. It's in their behavior. But for our purposes, I want to say, if we're going to talk about a nucleophile, we're talking about something that wants to form a bond to a carbon, that can form a bond to a carbon, given a circumstance like that. And a base will mean a chemical species that can abstract a proton from an organic molecule. Remember, the subject here is not acid-base chemistry, it's really about the chemistry of organic compounds. And for our purposes, when we say add a base to that compound, the job of the base will be to abstract, to pull a proton away from the organic molecule. Okay, now let me describe the reactions that are characteristic of alkyl halides. They all derive with this tendency to let go of what organic chemists call a good leaving group.